Well, hello everyone. Today's topic is quite straightforward. It's a planetary equilibrium temperature. It's a widely used equation in astronomy, and I think most of you know this equation. Most of you are very aware of the formula. I'm just going to show you the simple derivation. So let's assume that we have a sphere, we have a star. Let's say the sun. We have the sun. Let's try to draw the sun. Let's say it has a radius r. So what will be the whole area? It will just be the 4 pi r square, the whole surface area. Yeah. Now let's imagine that a planet is orbiting the sun at a distance t. Let's say this distance is t. Now, what do you know from the Stephen-Boltzmann law? We know that uh, the luminosity is the Stephen-Boltzmann constant times the area times the absolute temperature to the power 4. Now we can rewrite this as 4 pi r squared t to the 4th. Okay. Now, what will be the energy received in this at this location at t distance? Obviously, it will not be this energy. It will decrease, right? Because it's being dissipated over over a circle with over a sphere with a radius of t. So that will be, let's say that energy, let's say the flux will be luminosity divided by the surface area of that sphere, which should just become the 4 pi's cancel out. We are left with sigma pi, sorry, not pi, sigma r squared t to the 4th divided by t squared. Yeah, now that's a fairly straightforward equation. Now let's go back to our planet. What's happening on our planet? So let's say this is the planet. Let's say that it has a radius of rb. Now, if there's a sun and it's giving off some, let's say, some energy, it's only one side, one surface that's receiving that light, right? So the surface area that we're going to use will be pi r squared, because it's just receiving sunlight in one direction. So it's pi r sub p r sub p square. So now, what will be the received energy? We have to figure that out. Now, before figuring that out, we have to introduce a new concept. It's called albedo. So albedo is basically represented with alpha. It means the amount of energy that's reflected. Yeah. Now, okay, from now on the derivation is quite simplistic. What will be the luminosity of the planet? Yeah, we can easily find that out. Let's say the LP is 4 pi r p square sigma. Yeah. Temperature of the planet to the power 4. This is actually the energy that the planet is giving off. Now, what is the energy that it's receiving? We can easily find it out. Um, it'll just be what we have in the previous page. This amount, right? We're gonna have to use that. Let's be power 4 divided by d square, which this will be multiplied by this area. Now we also have to introduce the albedo. So what is the amount of energy that's not being reflected? 1 minus alpha, right? Now we can actually do one thing. We can set both of them equal, right? Because they will be equal. This is the power that it's receiving, and this is actually the power that's being dissipated. So we can set them equal. Let me do it. Sorry. Let me do it here. So from each side we can cut this with this. If we simplify this, we should get something that looks like this. So let's use this denotation. Yeah. We also use this for the R. Makes it much more convenient and easy to spot, right? Yeah, so this is a planetary equilibrium temperature that we were talking about for such a long time. And this is its derivation. This will be all for this video. I hope uh, I didn't make too many mistakes, and obviously I didn't stutter much. Uh, Thank you for watching.